Welcome back, guys. Today we are going to start the three-phase power transformers. Before we start the three-phase power transformers, let us go back and recap what we've done so far. In the last two videos or two lectures, we discussed the power transformers, an ideal power transformers, a practical single-phase power transformers. We also determined the circuit representation of a single-phase power transformers. We took into consideration the core losses. We took into consideration the power losses due to the winding primary and secondary, and also we completed the circuit as seen from the primary as well. We did also an example. Today we are going to talk about three-phase transformer. What's a three-phase transformer? Three-phase transformer is made of three single-phase transformers. So I have a single-phase transformer, identical. I get three single-phase transformers, and I connect them in a way to form a three-phase. For a three-phase system, I have four different types of connections. For a three-phase system transformer, I have either delta Y, I have Y, Y, I have Y delta, and I have delta delta. This is the primary side. This on the primary side, that's a transformer. So I have four different types of connection. I have primary could be delta, secondary could be Y. I have primary could be Y, secondary could be Y connection. Primary could be Y, secondary could be delta, and the final connection could be delta on the primary, delta on the secondary. Now it's very important to note that every country has its standard of nominations. For example, in the United States, under the American standard, the primary or the high voltage side, they refer to under the American standard. I have the high voltage side notation is H1, H2, and H3. These are the notation for the high voltage side of the transformer terminals. On the low voltage side of the transformer terminals, the notation is X1, X2, and X3. These are the notations under the American standard. Let's take a moment to digest this information. So what we studied in the previous chapters regarding the power system, delta Y, Y delta, all the circuit analysis that we did under the previous chapters for a three-phase system still valid. Nothing will change. Same circuit analysis, same calculations will still apply. Now, let's see how do we connect three-phase transformers using three single-phase transformer. This connection will help us to perform our lab, to perform our future simulation using engineering software. Let's start. Okay, now I want to sketch three-phase transformer. That's single-phase transformer. This, get a different color pen. Okay, this is one phase. This is your second single phase transformer. This is, and the last one this represents three single phase transformers. I have transformer 1, transformer 2, transformer 3, single phase. Now, I'm going to connect this transformer. For the first case, I am going to connect Y on the primary, Y on the secondary. Pay attention how I do the connections. Pay attention. Y, how do I represent Y? This is my windings connected to this windings, connected to this windings. This is my Y connections. So what I do is I take one side of the windings connected into here. This I establish the connection for the Y, and this will become A, B, C. This is now my primary side connection as a Y. It's worth noting that in many books or many countries, they will have A, B, C, capital A, capital B, capital C as a primary values, and then on the secondary values they have small a, small b, small c for notations. Now the second side I do exactly the same. Look, I connect, this is my Y, and this will become A, B, C. Oh. That's how now I connected three single phase transformers to form Y connections. Okay, is that clear? I hope that's clear to you guys how I use three single phase transformers to connect it into Y and Y. Now, I want to connect Y delta. This is the first Y. I want to go ahead now and connect Y to delta. So this is my three phase. Connected Y delta. Y I leave it the same as I did before. Now, what's a delta? What's a delta connection? What's a delta connection? Delta connection, if I look at this, I have one phase connected to another phase, connected to another phase. This is my delta. That's my delta. So if I call this 1, 2, 3, 4, 5, and 6, each one I have 1, 2, I can call this 3, 4, 5, and 6. So what I do is now I connect 2 to 3, 4 to 5, and then 6 will be connected to 1. See, 1 to 6, and this now provide to me my connection as a delta. Where's my output? I have now, this is my small a. From here, I have my small b. From here, I have my small c. These are my connection. That's now how I connect Y delta. Of course, I can connect delta Y. It's the same concept. Let's do one more. Let's do delta delta. One more. Delta delta. So I need to get rid of this Y connections. And I am going to connect this as a delta delta. So what I do is this one will be connected to this one. This one will be connected to this. This type will go all the way down to here. This is A, will remain. This will become B. Remember, this is the same node, and this will become C. This is that's what I have, delta connection. Delta connection. Now, guys, this is clear from this transformer connection. Let's do one more type. Let's use the circuit representation. If you're using any simulation tools, you might see this notation. This is a single phase transformer. This is single phase transformer. This is single phase transformer. And this is single phase transformer. See, this is to connect YY or delta Y, to connect, for example, Y delta. I'll follow the same. I'll connect this side to this. I'll connect this side to this side. This will become A. That's what will become B. And that's what will become C input. On this side, delta, I do the same. This will be connected to this point, this terminal to this terminal, and this terminal like this. And I'll have small a in here, small b in here, small c out. How can I connect the voltage on this side? Look, if I have a voltage now, that's a V angle 0. I have another voltage, V angle minus 120. I have another voltage, V angle plus 120. I connect this into E. This is my B. And this is my C connections. Because I have a star connection, I can connect this to ground as well. Because I have Y connection. This is a positive sequence. We studied this before. Positive sequence, negative sequence. A, B, C. The B is minus 120 degree, C is plus 120 degree shifted. That's for a balanced three-phase transformer. I hope that's clear. One more element before we finish this topic. Remember the 30-degree phase shift. Do you remember? Okay. If I have a voltage, let's get a look at this. I want to convert now from phase to Y. Let's take a moment to recall what we studied before. So what we did before in regard to, let's say I have, this is a positive sequence. I have V, A, N, that's V, C, N, and that's V, B, N. These are the three phase voltages of a positive sequence. That's a phasor diagram. When I want to convert this phase to a line voltage, what I have to do is this will be shifted by 30 degrees. That's a VAB, it's equal to root 3 VAN angle 30 degrees. This is because I shifted by 30 degrees, I take this will be now minus 120 degrees. That will be VBC. And I have the last one. This will be 120 degrees. Shift, and that will be VCA. It's a VCA. So this is very important and never changed for what we learned previously in the previous chapters when it came to a three-phase analysis. This will remain. So I have to be very careful. Let me show you now. Let me show you how this is applied into the transformers. Pay attention. Pay attention. If I have a delta, I think this will be clear on this side. If I have that's a delta transformer. And the second side of the transformer is Y. Second side of my transformer is connected into Y. I call that IA, IB, IC. I call this I small a, I small c. If this current, if I take this current as a reference, it's equal to I angle 0. This it's equal to I angle of minus 120. This is equal to I angle of plus 120. This magnitude, you can remember the transformer, this transformer, this current, because it's a phase, it's the same current, so there's no change. What will happen is this current in here, irrespective of its magnitude, or this current in here, will have the same phase current as this value. However, in here, will be shifted by 30 degrees. This one will be shifted by 30 degrees. So if I take this as a reference current, this will be shifted by 30 degrees. If I take this as the reference current, this will be shifted by 30 degrees. The answer, I have to always keep it into consideration. The reason is inside the transformer, remember, these are windings. If I go back to what I did into E, remember the three connections? This current is in respect of the actual current goes inside the windings. So this current is in respect of the current that goes inside the windings. That's why this current and this current will have the same angle shift. However, this will be shifted. I hope that's clear. And we will do a lot of examples. I will upload online a lot of examples where we can do it together during the revision session or during the actual calculation session. I hope that's clear. Is that clear now? How do I establish a three-phase transformers using three single-phase transformers? I hope that's clear. Now, the next step, after we studied now the single-phase and the three-phase transformers, we did an ideal and a practical. Now, it is important to go into the per unit. And that's what we are going to do in the next lecture, next video, or next section. I hope that's clear. Let's now pause it and do some example.